Okay, welcome back. We're talking about the discrete time Fourier transform and its properties. And in front of me here, I have one of my favorite textbooks, or my favorite textbook, Signals and Systems, second edition by Oppenheim. Any good reference material will have a table of the properties. You know, any good textbook, any good internet site will have a table of these properties. And if you notice in my table of contents, this book has a chapter on discrete time Fourier transform, and then down here, section 5.6, tables of transform properties and basic pairs. So I'm going to go down to that, and I'm actually going to look at the pairs first. And I'll remind you of how it is that we use these properties. What we do is we take a complicated looking signal, you know, the signal whose transform we want, and we see if we can relate it to basic shapes and formulas that whose signals we've already, or whose transforms we've already calculated. Then if we can find that relationship, then we apply properties to quickly get the transform of the more complicated signal it is we're looking at. So here is a table of common transform pairs. So for instance, e to the j omega 0 n, here's its transform cosine, here's its transform sine, transform 1, there's the transform periodic square wave, impulse train, a to the n u of n, right? We calculated a lot of these things already. All right, so let me scroll up, and let's go to, here's the properties of the discrete time Fourier transform. So you'll see here's the aperiodic signal, and then here's its Fourier transform. So something like, before we get to the properties, it says, okay, suppose x of n is has Fourier transform x, e to the j omega, and y has Fourier transform y, e to the j omega. Then, you know, we've got linearity. A times x plus b times y is a times capital X plus b times capital Y. Time shifting, which we didn't talk about, but it's the same thing as continuous time. Shift by n0, and then that has the effect of changing the phase of the Fourier transform. And then there's the dual to that, frequency shifting. So shift in frequency multiplied by e to the j omega. Conjugation, which we did not talk about for discrete time, but we did for continuous time. Those properties remain the same. Time expansion, we talked about. Convolution and multiplication are dual properties. There they are. Differencing in time we covered. Accumulation we did not, but there it is. Differentiation frequency, and so forth. And here's the symmetry for, you know, the conjugation and for real and even signals, and those are the same or very similar to continuous time. And then there's Parsifal's relation, which is again very similar to continuous time. So there you have it. You should find some sort of reference material that you can use, maybe your textbook, maybe some textbook, maybe some online reference material, but you should be able to find something that you can rely on here. In the next couple of videos, we're going to look at some concrete examples of how we can apply these properties of the DTFT, so stay tuned.